Okay, let's start with the question. So the last topic that we have finished was this electric field lines. I'm drawing a field line using this field line pattern. Decide first part. The nature of charge Q1 and Q2. Nature of charge Q1 and Q2. Second, neutral point. Third, the nature of charges Q1 and Q2, we have to decide the neutral point and compare the magnitude of charges. Which one is stronger? Compare magnitude of Q1 and Q2. You just have to decide out of Q1 and Q2, which one is the stronger charge. Q1 and Q2. Q1 is positive or negative?
Q1 is positive.
Q1 is positive, right? Why is it positive?
Because the direction it starts from positive and ends with negative charges.
Good. So the first is positive and negative. So that's the answer of the first part. Huh? That Q1 is positive charge and Q2 is negative. So the answer of first part is Q1 is a positive charge and this Q2 is negative charge. Second part. Neutral point.
B.
Yes. At neutral point, the field lines becomes parallel. Field lines are parallel over this point B, not at point B. See here, field lines are not parallel, but at B it's parallel. So the neutral point is B only. Neutral point is B. Okay, Afroza, which one is the stronger charge? Is it Q1 or Q2? Stronger one. Which one is the stronger charge? Is it Q1 or Q2? Yeah, Q1 have more field lines. Q1 is stronger. Q1 is stronger than Q2. So that was the first question. So up to last class we have completed electric field line. The next topic is force on charged particle. Force on charged particle in uniform electric field. So say you have a uniform electric field. This is a uniform electric field. It's a uniform field. In this uniform field, let's place a charged particle. Say I place a charged particle plus Q in this field. So this field is external. For charge Q, E is external. E is an external field for charge. For charge Q, E is external. Which means this E field is not generated by charge Q. So if you place a charge Q in an external field, this field will exert force over charge Q. If the charge is positive, then field will exert force over the charge in the direction of field. If the charge is negative, then field will exert force over the charge in a direction opposite to that. So electric field exert force on charge. So whenever you place a charge in electric field, then electric field will exert force on that charge. For positive charge, if the charge is positive, for positive charge, direction of force is same as that of field. While for negative charge, the direction of force is opposite to that of field. And the magnitude of force is this, F is equal to QE. This is the magnitude of force on the positive charge, QE. And the direction is same as that of electric field. But instead of positive charge, if you have a negative charge, for negative charge, direction of force is opposite to that of field. So for negative charge, direction of force is minus of qt. So direction is exactly opposite to that of field for a negative charge. So this is of field exert force over charge. So if your field is uniform means neither magnitude nor direction of field will change. So if your field is uniform, that means these forces are constant. So if field is uniform, then force is constant. The magnitude and direction of force will not change. So if your field is uniform, if m is mass of charged particle, m is mass of charged particle, then acceleration of charged particle can be written as acceleration of charge q. Acceleration of charge q is the ratio of force and mass. The acceleration is the ratio of force acting on the particle and mass. So the acceleration is q equal. So the magnitude remains same whether the charged particle is positive or negative. It will not affect the magnitude. Magnitude will remain same, but direction depends upon the nature of charge. So if you have a negative charge, then the direction is just reverse. So this is acceleration. Here, see, q is constant, it doesn't change. E is uniform, so the value of E will not change. Mass will not change. So you can say that this acceleration is uniform. And you can say that your motion is uniformly accelerated. Motion is uniformly accelerated. So the motion is uniformly accelerated. So if motion is uniformly accelerated, then you can use three equations. Like for uniformly accelerated motion, you can use this equation, V is U plus AT. You can even use this equation, S is UT plus half AT square. You can even use this equation that V square minus U square is 2. So the type of questions that we get from this particular topic, there are two types of questions. One is based on straight line motion. The straight line motion that you did in chapter number 3 of class 11, uniformly accelerated motion. And then there is one more type of question which are based on two-dimensional motion that you did in chapter number 4 of class 11, that is projectile. So from this particular topic, you will get two types of questions, one in motion in straight line and another motion in plane, two-dimensional. Let's start with numericals on this one. So the first question is, you have a charge, a body of mass sum m and charge q. Let's write this as a body of mass 10 gram and having charge of say minus 2 millicoulomb, the negatively charged body, remains in equilibrium in space having electric field. Predict the magnitude and direction of electric field. Magnitude and direction of electric field. So this is mass m. This mass m will experience a force due to its weight, and this weight will try to move this mass m in the downwards direction. To balance this weight, you need a force in the upwards direction, an electric force in upwards direction. This electric force is applied by electric field. Now the charge is negative. This negative charge will experience force in a direction which is opposite to that of field. So if you need force in the upwards direction, that means your field should act in downwards direction. So this is the direction of field. Your field should act in downwards direction. Then only force will act in upwards direction on the negatively charged. So in equilibrium, this electric force should balance the weight. So you can write that in equilibrium, electric force is equal to weight of the body. Electric force is QE, the weight is mg. So you can get E is mg by Q. Now you can easily substitute the values. Right? Mass is 10 grams, so that's 10 into 10 raised to the power minus 3. G is 10 meter per second square. Charge is 2 millicoulomb, so that's 2 into 10 raised to the power minus 3. Gets cancelled out. So the electric field is 50 Newton per coulomb. And the direction of electric field is just opposite to that of force. That means field is acting in downwards direction. So in vector form, we can use a unit vector minus j cap. So it's 50 minus j cap Newton per coulomb. So this is the electric field acting over the charge. The next question is on one-dimensional motion. So you have two plates. One is positively charged, another is negatively charged. So electric field exists from positive to negative plate. So this is the direction of electric field. Okay, let's place a proton at this point. It's a proton. So in which direction this proton will experience force? It will experience force in a downwards direction or in the upwards direction?
Downward.
Downward. This will experience force in the direction of field. The separation between the plates is d. So proton will experience force in downwards direction. And you also place an electron here. Electron is negatively charged particle, so it will experience force in opposite, in a direction opposite to that of electric. You're supposed to calculate time taken by proton and electron to strike another plate. So let's start with proton. Proton will experience electric force in the downwards direction. So the force on electron is simply charge of proton multiplied by electric field. So proton will experience force in the downwards direction, and force is simply charge into field. Next, you can calculate acceleration of proton. The acceleration of proton is simply force divided by the mass of proton. So this is E over mp. I'm not substituting the values of E and mp here, because this capital E is not given. There's no point in substituting numerical values. We will solve this in alphanumeric terms. We will solve this in terms of E, capital E and M. This is acceleration. Next, to calculate time, you can use this equation. S is ut plus half proton acceleration into time square. Proton was initially at rest when it was placed over this point. Is was initially at rest before application of electric field. So you can say that initial velocity of the proton is 0. I'm repeating again. Before the application of electric field, your proton was at rest. So the initial velocity of the proton is 0. So can you just tell me the displacement that proton have to cover to strike the another plate? Yes, it will cover displacement d. So if I keep on substituting the values, instead of s, let's substitute d. Initial velocity is 0, plus its half, acceleration of proton, which is E over mp multiplied by t square. So from here, you can calculate the value of t. So this is twice of mass of proton into d over E is t square. So you can calculate t here. It's time for proton. It's 2 mpd by E. Okay, if I repeat the same calculation for electron, so the force experienced by electron is again E. The only difference is electron will experience force in a direction opposite to that of field, so it will move upwards. The acceleration of electron is E by mass of electron. Instead of mass of proton, we are using mass of electron. Again, the displacement that it will cover is the initial velocity of electron is 0. You can use this equation. S is ut plus half acceleration of electron into t square. So displacement is d, initial velocity is 0, it's half. Acceleration of electron is E by mp over te square. So the te comes out to be twice of mass of electron into d by E. This E is in subscript. Okay, this shows mass of electron. This E is in subscript, twice of mass of electron into d. So this is the time taken by proton to reach this plate, and this is the time taken by electron to reach plate. So who will arrive first? Proton will reach the other plate, or this electron will reach the other plate first? If I say which one will win the race? Which one will win the race? The time taken by proton depends upon 2, D, E, E, and M. This is mass of proton. The mass of proton is 1.67 into 10 raised to the power minus 27 kg. This is ME, mass of electron, which is 9.1 into 10 raised to the power minus 31 kg. All other parameters are same, but the masses of proton and electrons are different. So can you just tell me for which one of them the time is less, will take less time to reach the other plate? Why proton? The mass of proton is less than that of electron. Say the mass of proton is minus 27 and that of electron is minus 31. Means mass of electron is 1000 times less than that of proton. Mass of electron is 1000 times less than the mass of proton. The time is directly proportional to the masses, right? So the particle having smaller mass will have smaller time. They are directly proportional. Since mass of electron is less than mass of proton, so time taken by electron should be less than time taken by proton. Is it clear? Yes, Fatima, you should memorize this value. Yes, mass of proton and mass of electron. More than physics, you will need these values in chemistry. In physics, you will need these values as 1 or 2 numerical, but in chemistry, you will need these values. So since mass of electron is less than mass of proton, so time taken by electron is less than the time taken by proton. Now, can you decide who will win the race, the proton or electron? Say two athletes, athlete A and athlete B. They start from the same initial point, and this is the final point. Athlete A takes 2 hours to reach this point. Athlete B takes 1 hour to reach this point. So, what do you say, that athlete A win or B win?
B.
Why B?
Because it took 1 hour.
It's taking less time. B is taking less time. So, if your logic works in the case of athlete, then what's the problem with this proton and electron? Since electron is taking less time to reach the opposite plate, the time taken by electron to reach the opposite place is less than that of proton. Then don't you think that electron will win the race?
Yes.
Proton is taking 2 hours, then electron will take less time. Maybe it will take 100 times less time than that of proton. So who will win the race?
Electron.
Electron will win. This is a solid example of NCRT. Electron will. The next question is basically it's an problem of NCRT. Chapter number 1, the problem of back exercise. So in the question, it's given that you have 2 plates and an electric field that exist in this direction. This is the direction of field. The length of the plates, the length of the plate is L. A positively charged particle, a particle having charge Q, it enters this field with a velocity v along x-axis. Charge Q enters this field along x-axis, but field along y-axis. Now, in which direction this charge Q will experience force? In which direction will this charge Q experience force? It will experience along x-axis or along y-axis?
Y-axis.
Along y-axis. Charged particle is a positively charged particle. It will experience force in the direction of field. Padma, field is not along x-axis. Field is along y-axis. So the force that it will experience will be along the field, that is y-axis. See here, the initial velocity of particle is along x-axis, but the force that this particle experiences is along y-axis. So can you just guess what should be the path of particle? It would be a straight line path or a two-dimensional. We move in two-dimensional path. Straight line. See, the path will not be straight line. It cannot be straight line. See, say if you have a particle, it's moving along x-axis, right? But you are continuously applying force along y-axis. So what will happen to this particle? Along with x-axis, it will slowly deflect, keep on deflecting towards y-axis. It keeps on deflecting towards y-axis due to this particular force. And it is also moving along x-axis. Like if it moves in this way, that means it's moving only along x-axis. If it moves in this particular way, that means it's moving only along y-axis. But the charged particle moves in this way. That means it's moving along x-axis as well as y-axis. So this charge q is moving along x as well as y axis. So it will move in this way. Due to this component of velocity, it will try to move along x-axis, but this electric force will push it along y-axis. So this is how the particle will move. This will move in this way. Sorry. You're supposed to calculate the deflection. This is the direction of initial velocity. The direction of initial velocity. And this is the point where this particle moves out of the field. So along y-axis, this deflection is y. In this particular numerical, you're supposed to calculate this deflection of charge particle. So the question says, a charge q move in electric field as shown in figure in a direction perpendicular to length of plates is L. Calculate deflection of charge particle. Deflection of charge particle when it moves out of the field. So when the charge particle moves out of the field, then you're supposed to calculate this y deflection. I'm giving some hint. Try solving this problem along x and y axis separately. From x axis, try to calculate time and then substitute in this y equation. Let's first solve along x axis. So, okay, Afroza, what is initial velocity along x axis? What is the initial velocity of this charge particle along x axis? See, since it is initially, the velocity is along x axis only. So the whole x component of velocity initially is v. So Afroza, what is the force along x axis?
It won't experience any force.
It will not experience any force. A charge particle experiences force in the direction of field. The field is along y axis. Huh? There's no field along x axis. So it will not experience any force along x axis. The force along x axis is 0. If force is 0, that means acceleration along x axis is 0. Okay, can you just tell me a displacement along x axis covered by the particle when it moves out of the field? The displacement covered by the particle along x axis when it moves out of the field. L, very good. Along x axis covering a displacement L. So when it moves out of the field, it will cover a displacement L. From this equation, we can calculate time taken by the particle to move out of the field. So let's say t, it's time taken by charged particle to move out of the field. Out of the field. So we can write this as v is not v. We can use this equation like S is ut plus half at square. If we keep on substituting the values, the displacement that this charged particle will cover is L. The initial velocity is v, time is t, the acceleration is 0. Sx, ux, ax. This x in substitute simply shows that things are along x axis. So the value of t is L by v. That is equation number 1. Okay, if we take motion along y axis, Fatima, what is the initial velocity of charged particle along y axis? Fatima, can you just guess the initial velocity of charged particle along y axis?
0.
0. Why is it 0?
Because it starts from the.
Because it starts along x axis, right?
Yeah.
If it starts along x axis, then the y component will be 0. You can see, if you have a vector A along x axis, then the y component of vector, this angle is 90 degrees. So for y, you will write this as a cos 90 is 0. So y component will be 0. So if initial velocity is along x axis, then the y component of initial velocity will not exist. Its y component will be 0. Will it experience any force along y-axis?
Yes.
Yes, it will experience a force QE along y-axis. And acceleration along y-axis will be QE by m. Displacement along y-axis is what that you have to calculate. And the time taken by particle is same as that was along x-axis. Because you are studying the same motion. The same motion, let's call this point as O, and I call this point as P. You're studying the same motion from O to P. So time will remain same. Time will be L by. Try to calculate Sy now. I need Sy. So to get displacement along y-axis, we can use this equation. Second equation of motion, S is ut plus half at square. You can use this equation. S is ut plus half at square. When you're using this equation along y-axis, just write y. So what is Sy? Sy is something which we have to calculate. Uy is 0. It's plus half Ay, which is QV by M. And then this is T. T is L by V whole square. So this is the deflection. QE L square by 2M. This is displacement along y-axis. Okay, so that was motion of charged particle in a magnetic electric field. So in a uniform electric field, this charged particle will experience force. These are the three types of questions that you will get based on this concept. The first question is on equilibrium. The second one is on one-dimensional motion. The third one is on this two-dimensional motion. That's an important question. Now the next is, what will happen if instead of a point charge, I place a dipole in uniform electric field? Dipole in uniform electric field. Dipole in uniform electric field. If instead of a point charge, I place a dipole in uniform field, so this is uniform electric field. So in this uniform field, I place a dipole. Dipole means a system having equal amount of negative and positive charge. I place the dipole in this uniform field. Dipole simply means it's a system which is having equal amount of negative and positive charge. So this positive charge will experience force in the direction of electric field, which is QE. The negative charge will experience same force in a direction which is opposite to that of Q, which is minus of Q. And if you talk about the direction of dipole moment, the direction of dipole moment is this. It's always from negative to positive. Angle between dipole moment and electric field is theta. This angle is theta. This 2 is theta. So consider an electric dipole in uniform electric field. Electric dipole in uniform electric field. So first of all, let's calculate net force on the dipole. Net force on dipole. So the net force is simply the sum of force on positive charge and negative charge. So it will be the vector sum of QE and minus QE. See, you can see that QE and minus QE will cancel each other and you will get that net force is 0. So the net force acting over this dipole in the uniform field is 0. This dipole will not experience any force. If it will not experience any force, that means no translational motion. That means no translational motion. Means no straight line motion. If this is the dipole, it can't translate, means it can't move along x or y axis. It can't translate, this will remain over its own, on its place. There's one more possibility. Due to these forces, this dipole can rotate. Due to these two forces, there's a possibility that this dipole will rotate. Say a force is acting along positive x-axis and another force is acting in opposite direction. It can rotate. This dipole can rotate. Okay, can you tell me what is torque? See, we need force for... Yes, Juvena, you're saying something.
A body has different, not just many points
Mhm. No. That is rigid body. Torque is something which can rotate a body. Say, if you can see this pen, to translate this pen means to move this pen along x-axis, you need force. But to rotate this pen, you don't need net force, you need some torque. So torque is something which is required for rotation. Torque is rotational analog of force. Torque is rotational analog of force. So whatever force do in straight line motion, the same thing torque do in rotational motion. So we call torque as the rotational analog of. So if a fan is rotating, it's rotating due to torque. A torque is acting over the fan, which is rotating that. So torque is rotational analog of force. So there's no rotation, translational motion if net force is zero. Now see, this force QE and minus QE both have same magnitudes, but they are acting in opposite directions. So we can say that a couple is acting on the dipole. In mechanics, couple simply means a system having equal and opposite forces. You can see it's clear that at point charge plus Q, a force Q is acting, and for charge minus Q, force minus Q is acting. Both the forces have exactly same magnitudes but opposite directions. So these types of forces make a couple. So a couple is acting on the dipole. And remember one more thing. Whenever a couple acts on a dipole, that couple tries to rotate this dipole. So this couple will exert torque over dipole. So this couple exert torque. This couple will exert a torque on the dipole, and that torque can rotate it. This couple will exert a torque on the dipole, and that torque can rotate it. You can write this torque as no. Couple simply means equal and opposite forces. Like if I take this body, I apply a force of 2 Newton in this direction and a force of 2 Newton in exactly opposite direction. You will say that a couple is acting on the body. Like if I'm opening the cap of this bottle, if I'm trying to open the cap of the bottle, then I'm applying couple. Applying, if you say this is the bottle, I'm applying a couple over it. I'm applying two forces equal and opposite. By my thumb, I'm trying to rotate it in the anti-clockwise direction, and the rest of my hand is trying to rotate in the clockwise direction. So there is one force in the backward direction and one force in the forward direction. So this couple will exert a torque, and the bottle, this cap rotates and the bottle opens. So couple doesn't mean charge here. Couple means forces. Couple means equal and opposite forces. It's basically in class 11 there was chapter number 7, which was rotation. In rotation, you must have done these terms like couple, torque, and all. So is it clear? Couple, what is couple acting on the dipole? What do you mean by couple acting on the dipole? So couple simply means the net force acting on the dipole. And this couple will exert torque. This couple will rotate this dipole. That means this couple will exert some torque on the dipole. Now, we can calculate torque. We represent torque by tau. This tau is the notation for torque. Torque for a couple is the product of its magnitude of any force. Now, since in couple both the forces are equal, so take magnitude of any one of them and multiply it by the perpendicular distance between them. The perpendicular distance between them. This is how we calculate torque. So see, in this particular example, in this case, this is point A, this is point B, this is first force QE, this is another force minus QE, this is the line of minus QE. You need perpendicular distance between them. This is the perpendicular distance between the two forces. This is the perpendicular distance. Perpendicular distance between the forces. Let's call it as N. So you can simply write your torque as magnitude of any of the force. This is the formula of torque. The way the formula of force is mass into acceleration. In the same way, the formula for torque is magnitude of any of force multiplied by the perpendicular distance between them. So here, you can take magnitude of any one of them, which is same, it's QE, perpendicular distance. Now, can you tell which one is the perpendicular distance between the forces? Is it AB, BN, or AN?
BN.
BN. So the perpendicular distance between the two forces is B. So that is my equation number 1. Now, we are supposed to calculate this value of B. Can I say that this line AB is the length of dipole? This is length of dipole, no? The separation between negative charge and positive charge. The separation between minus Q and plus Q is length of dipole. How we represent length of dipole? We did this thing yesterday. Yeah, 2A. Right, 2A. Huh? We represent length of dipole by 2A. So if we consider triangle A and B, in this triangle A and B, what is sine theta? Sine theta is perpendicular upon hypotenuse. It's BN over AB. So BN is perpendicular and the hypotenuse AB is 2A. So from here you can calculate BN. This is, we substitute equation number 2 in 1. Then you will get that your torque is X force QE. Sorry, from 2 you can calculate the value of BN. The value of BN is 2A sine theta. You can write your BN. Your BN is 2A sine theta. Let's call this as 3. We can substitute equation number 3 in 1. If we substitute 3 in 1, then your torque is X QE multiplied by 2A sine theta. This is torque. This is QE into 2A sine theta. And we can just combine this Q and 2A and write this as P. So your torque is PE sine theta. So this is the torque, which is PE sine theta. So this is the torque acting on the dipole, which is PE sine theta. Okay, this PE sine theta in vector form, this PE sine theta can be written as P cross E. In vector form, you can write this PE sine theta as P cross E. Okay, do you remember this cross product of vectors? There are two types of products of vectors, one dot product and another cross product. You remember this thing or should I revise it? We will use some properties of cross product. Okay. Afroza, Fatma, yes, you remember this thing. Fatma, yes means you remember this thing, I don't need to revise it. Huh? Okay. So this is the torque acting on the dipole. Now this torque will try to rotate the dipole. This torque will rotate dipole and will try to align it along the electric field. So the torque will rotate dipole and will try to align it along electric field. That is the motive of the torque. So whenever you place a dipole in a uniform field, a torque will act on the dipole and this torque will try to rotate the dipole and will align the dipole in the direction of field. So this dipole will rotate in this way. This is clockwise. Huh? The dipole will rotate clockwise and will try to get aligned in the direction of field. This is the motive of torque. This is how the torque will act on the dipole. So the torque will act on the dipole and this dipole will get aligned in the direction of field. So let's summarize everything. So whenever you place a dipole in a uniform electric field, the net force acting on the dipole would be 0. Dipole will not experience any force, but it will experience a torque. This electric field will exert a torque on the dipole, and that torque will try to rotate the dipole. Basically, this torque try to align dipole movement in the direction of field. So we'll try to rotate this dipole in a way that this gets aligned in the direction of field. Next, we have few special cases. Case 1. If dipole is, always remember the motive of torque. The motive of torque is torque will try to align itself in the direction of field. So if I say if dipole is parallel to electric field, if dipole is parallel to electric field, means this is electric field. This is electric field. And this is the dipole moment. It's parallel to electric field. If it is parallel, that means angle between them is 0 degree. If P and E are parallel, that simply means the angle between P and E is 0 degree. So whenever you place a dipole in a field, the net force is always 0. The net force will always be 0. But now it will experience a torque which is PE sine 0. Sine 0 is 0. So the torque acting on the dipole is 0. It will not experience any torque. Means neither it can translate, since net force is 0, so it cannot translate. Neither it will rotate. Since no torque is acting on the dipole, so it cannot even rotate. So you can say that your dipole is in equilibrium. Dipole is in stable equilibrium. So do you remember what is stable equilibrium? Stable equilibrium means
Net force is 0.
yeah, net force is 0, that's equilibrium. There was one more condition of stable equilibrium.
Oh yeah, body will regain its position.
But it will regain its equilibrium position. I gave this example of bowl. This is equilibrium position. If I disturbed it and if body regain its equilibrium position, then you would say that equilibrium was stable. So in stable equilibrium, body will regain its equilibrium positions on being disturbed. So here, if P is parallel to E, then it is in equilibrium. But if I disturb this P, now angle is not 0 degree now, then a torque will act on the dipole and this torque will try to align the dipole along the field. See, this is the initial configuration, that initially your dipole moment is parallel to field. If I disturb this dipole, then what will happen? If I disturb this dipole, then a torque will start acting over it and this torque will try to align this dipole along the field again. This torque will align the dipole along the field again. So after being disturbed, the dipole will regain its equilibrium position. Is it clear, this explanation?
Yes.
Initially it's parallel. If you disturb it, then the angle is not 0 now. Some non-zero torque will act on the dipole and that torque will again bring this dipole in the same position. That's why this is stable equilibrium. Case 2. If dipole is anti-parallel to electric field, if dipole is anti-parallel to electric field, if it is anti-parallel to electric field, means this is the direction of electric field and dipole moment is acting in exactly opposite direction. So Fatima, what is the angle between dipole moment and field? If they are acting in directions, how much?
0, right?
Not 0.
180.
180. 0 is when both the arrows are in same direction. But if arrows are in opposite directions, then the angle is 180. The net force is always 0. But the torque will be PE sine 180. So what is sine 180? Sine 180 is 0. Remember few values like sine 180 is 0. Cos 180 is minus 1. So no torque, no, sine 180 is not 1, it's 0. No torque, no force. So your dipole is in equilibrium. Dipole is in unstable equilibrium. Dipole is in unstable equilibrium. Unstable equilibrium means if you disturb this dipole. So if I disturb this dipole, then a torque will act on the dipole. In which direction will this dipole align? Once I disturb it, it will align parallel to the field or anti-parallel to the field. Just see, in the previous slide, I have written something about torque. This torque will try to align. See, just check the previous page. In the previous page, the torque was P cross E. Below this expression, I have written something. Just read that statement.
Torque will rotate dipole and will try to align it along the electric field.
Along the electric field. Along the electric field means P will be in the direction of field or in opposite direction.
Along the electric field.
Along means P is in the direction of field. So Fatma, see, along the field means in the same direction of field. Say we initially place the dipole anti-parallel. Angle was 180 degree, no force, no torque. So that's an equilibrium position. Now I disturb this dipole from this equilibrium position. Say angle between field and dipole is not zero now. It's not even 0 or 180. See, you can easily see now. This is P. This angle is neither 0 nor 180. So torque will act on the dipole. And we have written that this torque will try to align the dipole in the direction of electric field. This torque will try to align this dipole moment P along the field. This torque will try to align the dipole moment P along the field. Right? This will try to align the dipole in the direction of field. Now, since the initial and final positions are different, the initial position is dipole is in a direction opposite to that of field. But in the finally, this dipole moment becomes parallel to field. It's not achieving the initial condition. That's why I'm saying the equilibrium is unstable. Fatma, you have
Okay. Got it.
got it. So that's why the equilibrium is unstable. Jubaina and Afroza, is it clear this whole argument? Why is it unstable? It is because initially your dipole was anti-parallel to field, but when you disturbed it, then after being disturbed, it becomes parallel. It does not regain original configuration. That's why I'm saying this is the case of unstable equilibrium. After unstable equilibrium, there is one more case, case 3. If dipole is perpendicular to field, if dipole is perpendicular to electric field, so if dipole is perpendicular, that means this is electric field. This is your dipole. This is dipole moment P, this is electric field E, and this is 90. So the net force on the dipole is 0. But torque is not 0. This is PE sine 90. Sine 90 is 1. So the torque is PE. In fact, in this case, the maximum torque can act on the dipole. Is it the case of equilibrium? Can I say that dipole is in equilibrium when it is perpendicular?
No.
Can I say that dipole is in equilibrium if it is perpendicular to field?
No.
No. Because some torque is acting on the dipole and that torque can rotate. Okay, so the next thing is an electric dipole having dipole moment 2 coulomb meter is placed in a uniform magnetic field. Oh, sorry, not magnetic. Uniform electric field of 10 Newton per coulomb at 60 degree with respect to field. 60 degree with respect to field. Calculate torque and net force on the dipole. You need torque acting on the dipole and net force on the dipole. Solve this numerical straight formula based numerical. See, the expression of torque is just P cross E. So the torque is PE sine theta. Keep on substituting the values. Its P is 2, electric field is 10, multiplied by sine 60. So that's 20 into sine 60 is root 3 by 2. This 2 will cancel this 2, 10. So that is 10 root 3 Newton meter. This is the net force. The net torque, the net force is 0. This is the torque acting on the dipole, and the net force on the dipole is 0. For the next question, just you need a topic of class 11, which was SHM, simple harmonic motion. Simple harmonic motion. Let's revise this topic of class 11. We will use this topic in the next numerical. Simple harmonic motion. In fact, even in simple harmonic motion, we will use angular SHM, angular simple harmonic motion. The best example of angular SHM is that of a pendulum. If you take a pendulum and you disturb it, it keep on oscillating about its mean position. It keep on oscillating about its mean position. So this simple pendulum, motion of simple pendulum is basically angular SHM. So in angular SHM, the first point is your system oscillates. For angular SHM, system is in oscillation. For angular SHM, your system oscillates. This is an oscillation. Second, a restoring torque act on the system. A restoring torque acts on the system. So if you want to consider restoring torque in this case of pendulum, say this is the mean position of pendulum. This position is the mean position of pendulum. If I disturb this pendulum by an angle theta, what will happen to this pendulum, this bob of pendulum? This will remain in this position only, or will try to regain its mean position. If I disturb the ball of this pendulum to this position, it will try to regain its equilibrium position, which means a restoring torque is acting over. It tries to regain its equilibrium position. That means a restoring torque will act over. In the same way, if I disturb this up to here, it gets disturbed up to here. Then again, a restoring torque will act over it, and that restoring torque will try to bring it about towards the mean position. So this pendulum keeps on oscillating about its mean position due to restoring torque. And that restoring torque should be in this form. Restoring torque should be in this form, minus of k theta, where k is spring constant, where k is a constant known as spring constant. This negative sign shows that tau and theta are in opposite directions. See in this example again, theta is clockwise or anti-clockwise? So the orientation of theta, is it clockwise or anti-clockwise? This theta?
Anti-clockwise.
Anti-clockwise. And what about the restoring torque?
Clockwise.
Clockwise. So theta and torque act in opposite direction. That is given by this angle theta, negative sign. So negative sign shows that tau and theta are in opposite directions. Tau and theta are in opposite directions. K is spring constant. So tau is minus of k theta. So to prove that a system is in equilibrium, first you have to show that the system is in oscillation. Then you will have to calculate the torque acting on it, and then you will express that torque as tau is equal to minus of k. This is how we prove that a given system is in equilibrium.